and welcome to another WJEC A level physics question. This was from the Unit 4 exam in June 2012. It was question 2. It's about momentum and there's a little bit of wave-particle duality at the end. Momentum is now in Unit 1 and wave-particle duality in Unit 2 for the current specification. To start with, we have two gliders A and B on a linear air track, which is basically friction-free, and the first glider A of mass 0.2 kilograms is accelerated from rest by a force of 3 newtons for 0.15 seconds. And we're asked to show that the velocity of glider A after acceleration is 2.25 meters per second to the right. Well, possibly the easiest way of doing this is to apply the impulse formula, where force times time is equal to the change of momentum. And here, because the initial momentum of the glider is 0, the change of momentum is just equal to the final momentum. A little bit of rearrangement, and the final velocity will be F times t over m, force of 3 newtons, time of 0.15 seconds, mass of 0.2 kilograms, giving us the 2.25 meters per second that was requested. In the next part of the question, we're told that glider A collides with glider B, which was stationary. They stick together and they move with a combined velocity of 1.2 meters per second to the right. And we need to show that the mass of glider B is 0.175 kilograms. So let's set this up as a conservation of momentum question, where the total momentum before equals the total momentum afterwards. Before the collision, the total momentum we've got is glider A of mass 0.2 kilograms moving at 2.25 meters per second, and the total momentum afterwards is the combined mass 0.2 plus, let's call it m, moving together at a speed of 1.2 meters per second. We can work this out bit by bit. The left hand side will simplify to 0.45. If we expand the brackets on the right hand side, 0.2 times 1.2 will be 0.24, and we'll also have the 1.2m. If we bring everything that's not an m to the left hand side, we'll get 0.45, take away 0.24, which is 0.21, and that will be equal to 1.2m, and finally m will be 0.21 over 1.2, which will give you the 0.175 kilograms as required. In the next part of the question, we're asked to show in a different collision where the velocities of A and B are separately 0.15 and 2.4 meters per second after the collision, but the initial conditions were the same. We've got to show that the collision is elastic. Well, with an elastic collision there's no loss of kinetic energy. So if we calculate the kinetic energy before, we simply have half times the mass of glider A times its velocity of 2.25 squared. And that will give us 0.50625. But let's just take a couple of figures there and call it 0.51 joules. If we calculate the kinetic energy after, well, we have two objects. We've got object A of mass 0.2 kilograms moving at 0.15 meters per second squared. Sorry about that. And we also have object B of mass 0.175 kilograms moving at 2.4 meters per second squared. And if we put those numbers into the calculator, you'll get the exact same 0.50625. So let's call it 0.51 joules again. And the point is that the kinetic energy before is equal to the kinetic energy after, and that's why it's elastic. The question continues with a question about a scientist investigating the possibility of using a totally reflecting solar sail to power a small spacecraft. And sunlight of typical wavelength 500 nanometers, roughly in the middle of the visible spectrum, intensity 1500 watts per square meter, falls on a sail of area of 100 meters squared. The first part of the question is to calculate the energy of the photon, and here we can use hc over lambda, remembering that h and c are in the data book, and lambda here is 500 nanometers. So H 6.63 times 10 to the minus 34, C 3 times 10 to the 8, and wavelength here 500 nanometers. And we mustn't forget that nanometers is 10 to the minus 9. And by the way, remember that this equation is not given to you in the data book, so it's one that you'll need to remember. So plugging those numbers into a calculator gives us basically 3.98 times 10 to the minus 19 joules. On the second part of the question, we've got to determine the number of photons arriving at the sail each second. This is only 1 mark. In my opinion, it should be worth at least 2, because the first thing we need to realise is that because the intensity is 1500 watts per square metre, to find the total power arriving at the sail, we're going to multiply the 1500 by the 100 meters squared. So that's going to give us 1.5 times 10 to the 5 watts in total. And now to find our number of photons, we can just divide that total number of joules per second, which is what power is, by the energy of each of the photons to find how many photons we need per second to give that same total amount of energy. Sorry, just give me a second there. That gives us an answer of 3.77 times 10 to the 23. The unit is per second. Number of photons has no unit, but obviously time is measured in seconds. Now the last part of the question is to calculate the force exerted by the sunlight on the totally reflecting sail. Well, the point here is if we apply Newton's second law tells us that force is rate of change of momentum. So if we find the total change of momentum per second of the photons, then that would be equal to the force that the photons are experiencing from the wall. And if we apply Newton's third law, then the force that the photons experience from the wall, the sail rather, is the same as the size of the force that the photons exert on the sail. So first step, I'm going to work out the momentum of each photon using P equals h over lambda. Once again, h being 6.63 times 10 to the minus 34 and a wavelength of 500 nanometers. Again, don't forget the nano. So that gives us 1.33 times 10 to the minus 27, and that's kilogram meters per second. Now, since each photon is reflected, its total change of momentum is going to be twice that value that we've just calculated, and the total momentum change per second, in other words, the force, is going to be 2 times that change of momentum that we've just worked out, multiplied by the number of photons that hit that surface per second. So let's put in the figures. 2 times 1.33 times 10 to the minus 27 times 3.77 times 10 to the 23. And that gives us an answer very, very close to, in fact exactly equal to 1.0 times 10 to the minus 4 newtons. Sorry, 1.0 times 10 to the minus 3 newtons. Thank you for listening. Please like and subscribe.